When I was in university, I had a certain experience that happened to me over and over again. Primarily, it was anchored in math class. It went something like this. Show up to the lecture, professor would introduce something new, a formula, some tactic for approaching a problem, introduced on the whiteboard and explored through example problems, built up and knocked down repeatedly. I would understand all of these examples. I would understand all of these principles. But then would come exam time. I would crack open the exam and I would see a problem which practically cried out to be solved with those principles and practices I learned in the lectures. And so I'd dive right in. But 2 or 3 steps later, something would happen. There'd be a set of factors and they didn't quite cancel the way they should. There'd be a set of terms, but they didn't just nestle themselves into the formula that I had rushed in armed with. What I was learning through those math exams was something that's equally applicable to software engineering as well. And that's that problems in the real world don't line themselves up to fall on the sword of techniques that you pulled out of academia. Last year, I came to CppCon and I gave a talk on the Platonic principles of the networking TS, the things that it brings to us, the power it gives us to write asynchronous I/O code. And over the course of that talk, I took on the mantle of my professors. I built up an example on a projector this time, not a whiteboard, and knocked it down repeatedly. And behind the veil was the fact that that example had been tailored to demonstrate exactly those principles, and not the other way around. So please hold your questions to the end, because this year I'm back to take everything that was built up last year, the networking TS, and see how we can apply it to problems that actually occur in the real world, the kind of problems that fight back when you try to solve them. But first, let's talk about the networking TS. Because when I gave my talk last year, we were hopeful the networking TS would be in C++20, but that was not meant to be. Now we're looking down the barrel of C++23, which perhaps raises the question at once of why give this talk now? Why not wait 2 or 3 years until once again the networking TS looms large over the horizon? And the answer to that question, of course, is that Boost.Asio is the prior art on which the networking TS is based. And Boost.Asio is forward compatible with the networking TS. So if you like anything you see here today, you can just download Boost.Asio and you're off to the races as soon as you change a simple namespace. In fact, to take this one step deeper, if you wait until the last slide of this talk, you'll find a link to a GitHub repo. And that GitHub repo contains fully worked, unit-tested versions of every example on these slides and then some. Except there's no stdnet in any of those examples because they were all built, compiled, and run with Boost.Asio, and then when I moved them out of Vim and onto these slides, I just changed the namespaces. Now, I've talked a bit about the problem that I developed last year, but not everyone was here last year. Not everyone remembers. So let's talk about that problem. It was a composed asynchronous operation, which means that it took 2 lower-level asynchronous operations and layered on top of them some higher-level logic. And the higher-level logic was that the operation was named async wait then write. And what it does is write in the name. It waits for some amount of time, and then it writes some bytes. Last year, I used this exact sequence diagram to lay out what this operation did, and we're going to walk through this sequence diagram now. On the left side, as we enter the sequence diagram, we see this initiator. This is the person who kicks off the asynchronous work, who gets our operation started. Notice immediately that they have a very, very short lifetime. And this is endemic to asynchronous operations because when you initiate an asynchronous operation, you call an initiating function. It sets up some work to be done in the background, and then the initiating function is done. Your caller continues unimpeded by the fact that the I/O they set in motion may not yet be complete, hence the very short lifetime. Since this operation waits and then writes, the first thing we do is we kick off a wait on a timer. And that continues through time until it completes, and then we get something called a post against an executor. What could that possibly be? Well, if you think back when I talked just a moment ago about what an asynchronous operation is, I said that the work continues in the background. And people who want to ask a lot of questions will look at that and say, well, what do you mean background? Where is that? Whose thread is that? Who schedules those? How many of those threads are there? And the answer to that question, as with so many grand questions, is it depends. Because it depends on the executor that's being used. An executor is a shallow handle to an execution context. And an execution context is just something where callable objects can be run. It could be one thread, it could be a pool of threads, it could be something that none of us have even thought of yet. And the way you customize that is you form an association with something called a completion handler. A completion handler is a callable object which you inject into an operation when you initiate it. And by invoking this object, the operation reports that the operation is complete. So when the initiator initiated the operation, they gave us a completion handler. And that completion handler carried with it information about the executor that we would use to run background tasks. And now the wait is done, and so we need to run a background task, and so we post to the executor. At some time thereafter, the execution context services that post and invokes something called an intermediate completion handler, which layers another word on top of completion handler, does it? And that's because an intermediate completion handler is part of a composed asynchronous operation. A composed asynchronous operation consists of taking lower-level operations, stringing them together, and implementing some higher-level logic. In this case, we're not done the whole operation when we finish waiting. We need to turn around and then start writing. So rather than going off to the final completion handler and saying everything is done when it's not, our operation synthesizes an intermediate completion handler whose only purpose is to string these parts together. And sure enough, we turn around and we kick off an AsyncWrite on a socket. We've waited, and we need to write now. But then something curious happens. We see that inside write, we have these AsyncWrite sums proceeding in a loop. And that's because AsyncWrite used in this context serves to demonstrate something beautiful about the networking TS and composed asynchronous operations. A composed asynchronous operation doesn't just compose primitive operations like waiting, but it can compose operations which are transitively composed asynchronous operations, providing you the avenue by which you build small operations and then expand on them continually until eventually you've implemented your entire application. AsyncWrite, in this case, calls AsyncWrite sum in a loop until it succeeds at either writing all of the bytes or it encounters an error. At any rate, at some point in the future, it will complete. There will be a post to an executor, and at this point, we will have waited and then written. All the work will be done, and so we'll call the completion handler for our operation. We'll hand asynchronous control flow back to the person who initiated this operation in the first place and let them know you're done. Now, I promised a real-world snag, but if you look at this sequence diagram, you look at what it's doing, and you project it out into the principle, you can see that we don't have to compose waiting and writing. We can compose any two operations. And we don't have to compose two operations. We could compose three. And we don't have to compose three different operations. We could just close the loop like AsyncWrite does, and we could compose in a loop. We can generalize what I'm saying and say that this pattern can be used to compose any number of asynchronous operations in any way, provided we do so in series, borrowing some terminology from electrical engineering. And what we're saying is that the composition is unrestrained, except that we do one thing, and then another, and then another, and then another, and so on and so forth. But if you take this and you rush headlong out into the real world, it's going to hit you right in the face all of a sudden, isn't it? This isn't the only way you want to glue asynchronous operations together. You can't always solve your higher level problem by doing one thing and then doing another thing. Sometimes you have to do things at the same time. You have to coordinate between them. Let's think about those two operations that we composed on the previous slide, wait and write. We composed them in series, one after another. But if we take and suppose that we composed them in parallel at the same time, well, that would be the building block of something that is widely bemoaned as difficult to implement in the networking TS. Writing with a timeout. Let's see how we might take a stab at implementing AsyncWrite with timeout. We notice at once that this sequence diagram looks very different than the sequence diagram we just looked at. Our initiator kicks off two operations, and then both of those operations overlap and interleave with each other confusingly. And we follow along the branches of asynchronous control flow, and we discover, aha, the wait finishes first, and it calls an intermediate completion handler, which doesn't do anything. That branch of asynchronous control flow just ends. Because if we think about it, we can't call the user's final completion handler at this point. Because as I said earlier, the invocation of the user's final completion handler is a promise. It says to the user, all of the work is done. And all you have to do is look very perfunctorily at the sequence diagram, and you can see that all the work is not done. There's still a write going on somewhere. So this intermediate completion handler, it can't do anything. It has to just end. Rest assured that the higher level logic of the composed asynchronous operation will indeed invoke the user's final completion handler when that write wraps up. But we've run into another real-world snag here, because if you think about this sequence diagram and you think about a timeout operation, you realize that this sequence diagram is the failure case for a timeout. If your wait, your timeout ends first, well, that means that writing took too long and you timed out. And so if this were the canonical sequence diagram, the only one possible, we wouldn't write this function, because that would be an operation that always failed. And I don't know about you, but when I'm faced with an operation that always fails, I prefer to just write no code. It's a little bit more efficient. No, there's no reason to believe this sequence diagram is any more compelling than this one, except that the operations complete in the opposite order. And now we see that it's the write operation that does nothing when it completes, whereas the wait operation comes in and picks up all of the pieces. And what this means is that our intermediate completion handlers don't have a definite role. They have to dynamically pick up a role based on whether they are first or second to run. We've introduced an ordering problem implicit in the parallel composition. And what this means more deeply when you think about it is that we need some way for those two intermediate completion handlers to communicate with each other. You need some way for one to inform the other that I've already finished, so you need to pick up the pieces. We need a shared state. And then as we iterate through thinking about this problem deeper and deeper, we realize that we need a shared state for more than just this. Because when the write finishes first, that's our success condition. And the write is going to tell us how many bytes we wrote. And surely we want to turn around and give that to our user. But because we finished first, we need to wait to tell our user that things are done, so we need somewhere to put that value for the wait operation to pick up. And then continuing our thinking through of this process, we encounter an issue if we crack the networking TS open, because the networking TS doesn't say that completion handlers have to be copyable. Which means that we can't use the strategy we use in series composition, where we put the completion handler inside the intermediate completion handler. Because now there are two intermediate completion handlers, and so the question becomes, well, inside of which one? So instead, we pick one canonical place to put this completion handler in the shared state, the channel through which our intermediate completion handlers communicate with each other. Let's take all of this that we've built up and try and reify it in some code. We'll start at the beginning. This is the initiating function for AsyncWrite with timeout. We accept a stream to write to, the sequence of buffers we're going to actually write, the timer we're going to wait on to implement that timeout, and the duration of that timeout. And then we accept the completion token, which may seem mysterious at first, but it's part of the guarantees and patterns the networking TS passes through. For the time being, we can just pretend that a completion token is a completion handler, and we'll ignore the related boilerplate. If you're really curious about what it means, there's a section in the talk last year entitled Universal Asynchronous Model, which covers the purpose of these tokens and what you can do with them. The first two lines are, again, just boilerplate, and so I've elided them and we'll skip over them. And then we have three types whose definition I'm going to leave till later. That's our shared state and our two intermediate completion handlers. They only become relevant when the operation is completing, and so it seemed appropriate to pull them out and put them somewhere else, since right now we're just talking about the beginning. Line 80 is more networking TS boilerplate, and we can just hop over that. And then we grab ourselves an allocator to use to allocate the shared state, and we allocate the shared state on lines 82 and 83. Then the following three lines are us just getting things in motion. We want to write, so we call AsyncWrite. We want to wait, so we set the timeout of our timer, we call AsyncWait. And we lead out with more networking TS boilerplate. But as we reach the bottom of the slide, there's an unanswered question, something that I've glossed over that I probably shouldn't have. And that is line 81. I snap my fingers and suddenly I have an allocator. Well, where did that allocator come from? Who decided what that allocator is? This is an extension of what I talked about earlier when I talked about executors. I said that completion handler types carry with them implicitly an association between their type and a strategy for acquiring an executor. In this way, users, as their completion handlers pass through layers of asynchronous operations, keep their execution environment customized and in accordance with their requirements. And the networking TS provides exactly the same machinery for allocators. And so all we're doing on this line is going out to the networking TS, going out to its associator machinery and saying, I need an allocator. Here's the user's final completion handler. And sure enough, I get back an allocator, and I can use it to allocate my state. All the networking TS asks when we do this is that we're very careful to make sure that if we allocate memory with this allocator, we deallocate all of it before we call the user's final completion handler. But when you think about it, that's not really such a big ask, is it? If you allocate memory to do some work, and then you wait to call the user's final completion handler until you're done the work, which you have to do because that's what calling the final completion handler means, well, you should be done with that memory and you should have deallocated it. And then this provides a really nice guarantee for the user because it means that the user can provide you with something like a monotonic buffer resource. And when they get asynchronous control back, they can rest easy knowing that there's nothing in that monotonic buffer resource. I can just reuse that buffer. I can clear it as a no-op, or I can just let it go away. I don't need to do any checking. I don't need to do any validation. The guarantees of the networking TS just make it so. Now that we've got our operation off the ground, let's try and look at what happens as we try and bring it to completion. Let's take a look at our shared state, which is just a bag of values. We keep the write stream and the timer, references to them. And then, of course, we have to store the user's final completion handler somewhere, as we discussed, so there it is on line 13. And then we store the two values we're going to produce when we finish, the error code and the number of bytes transferred. And then we have a value called outstanding, which we initialize to 2. This is the number of outstanding operations. We set it to 2 because we have a wait and a write. The sum of those two things is 2. Looking at our intermediate completion handlers, we're faced suddenly with an entire slide of boilerplate code. We need somewhere to store the shared state, and then this allocator type and executor type, this get executor and get allocator. Those are part of that associator machinery of the networking TS. Because I said before, the associations are with the user's completion handler type. And I also said that those associations are maintained as that completion handler type passes down through layers of asynchronous operations. But we took that user's final completion handler and we stuck it in our shared state. And then we invented 2 intermediate completion handler types and we passed those through to our asynchronous operations. Which means that now the associator machinery of the networking TS, it doesn't see the user's final completion handler. It sees archetypes. And so we need to write this boilerplate to make sure that archetypes behave the same way as the user's final completion handler when you ask for an executor or an allocator. Getting down to the bottom of the slide, we have a constructor, of course. And then we also make sure that we're move constructible, and nothing else. Because the networking TS is silent on assignability, and we already know that completion handlers don't have to be copyable. With all that boring boilerplate out of the way, let's see what we actually do when a write completes, when the function call operator of this object is actually invoked. The very first thing we need to do is we need to disambiguate which of the 2 cases we laid out earlier we are in. Are we the first or the last operation to complete? And so we decrement the outstanding count since a write just completed, and so there's 1 less outstanding operation, and then we check that value. If it's not 0, that means that the wait is out there somewhere still, and it's going to come in and clean up after us. So we just propagate the values that we generated, and then we're very careful to throw away our handle to the shared putter. Because if we don't do this and this operation happens to live long enough, we won't clean up all of the memory we allocated with the user's allocation strategy. So we would violate those promises we made to the user. Now on the other, perhaps more interesting hand, if we find out that there are no more pieces of outstanding work, we actually need to complete our operation. But that involves deallocating the state. And some of the values we need are resident in the state. And so to avoid a use after free bug, we pick them out onto the stack. We reset the shared putter, thereby destroying the object. And then we call the user's final completion handler. And this wraps up the operation, except for the fact we haven't seen what happens when our wait expires. So here is another slide, a boilerplate. Exactly the same boilerplate with some find and replace done on it. And then we get to the interesting part of our timeout op. We decrement the outstanding count. We ferret away the appropriate value if we find that the write hasn't completed yet, which is an error code indicating timeout. because that's what a timeout means. It means that your wait completed before the thing you were trying to time out, and then we're done. Unless, of course, we were the last ones to complete, and then we have to pick some values out of our shared state, throw our shared state away, and wrap things up. Great. We composed in parallel, and we implemented a timeout operation. Or did we? Because in a timeout operation, when the timeout expires, the work you're timing out doesn't just keep going. But that's exactly what this operation does. When the wait operation expires, it doesn't stop you from writing, it just sits around and waits until you're done. That's the opposite of what a timeout operation does. And similarly, with a timeout operation, if you write really fast, you're not going to just sit around and wait for the timeout to expire, are you? But that's exactly what this operation does. So it's not a timeout operation. Because we've run into a problem with our model of asynchronous operations. Our model of asynchronous operations is one where we initiate an operation, and then the operation continues until it itself encounters a failure or success case. But we need another option, because we have another completion condition that we need to layer on from the outside. We need to be able to tell our write, I don't need you anymore because you timed out. And we need a way to tell our wait operation, I don't need you anymore because the write is already done. What we need is a way to cancel asynchronous operations. Fortunately, the networking TS provides exactly such a member function on each and every one of its I/O objects. It takes no arguments, you invoke it, and if that I/O object has any outstanding asynchronous operations, they end immediately. They end immediately with an error code which you can use to disambiguate cancellation from actual failure and actual success. So this wasn't really a real-world snag, was it? This was more like, I didn't read the documentation. Well, maybe. Personally, I've learned to distrust the real world, and when a solution seems too perfect, I look at it sideways. So let's look at a sequence diagram of what might happen when our timeout expires. So on the left here, you can see that at some point in time, we actually kicked off our write operation. And we know that our write operation is a composed asynchronous operation. It's composed of one or more calls to AsyncWrite sum. And so there is such a call, and it proceeds in the background, and it writes some bytes, and it completes. There's a post to an executor. The intermediate completion handler of AsyncWrite runs. It looks at the values it receives, and it sees that it wrote some of the bytes. So it succeeded, and it wrote some of the bytes, but it didn't write all of them. And so in accordance with the higher level logic that it layers on top of AsyncWrite sum, it goes back and it writes some more. And as it's going on writing some more, our timeout operation expires. That intermediate completion handler runs. It calls cancel on our stream. And it finds that AsyncWrite sum operation outstanding. So AsyncWrite sum completes. There's a post to an executor. And then sure, it didn't write all the bytes, but when it calls the intermediate completion handler of AsyncWrite, AsyncWrite discovers, yeah, I didn't write all the bytes, but this operation failed, so I'm done. And then our write op runs, finds it's the last outstanding operation, and completes everything. But that's still exactly what we want. We haven't found any real-world snag here yet. But the timeout that woke up and canceled us, that was something that the user provided to us. And so I can just imagine that I have some user who provides a longer timeout. And what that would mean is that cancel would happen a little bit later. And maybe when that cancel happens, that second call to AsyncWrite sum is already done. And maybe there was a post to the executor, but that underlying execution context, it was just really busy. Hadn't gotten around to doing that yet. And so when cancel comes along, it misses. There's nothing to cancel. And our timeout operation winds up and thinks everything is fine, and then AsyncWrite wakes up, sees that it wrote some of the bytes, but not all of them yet, and goes right back to writing. And the write just continues until it completes naturally, which is exactly what we set out to avoid at the beginning. Because what we were doing when we thought we could just cancel AsyncWrite is we were assuming that AsyncWrite was an indivisible asynchronous operation operating on the socket, which was wrong, and the incorrectness of that assumption is reified in this sequence diagram. So maybe we go out and we look at how AsyncWrite is actually defined. It's defined in terms of a concept, not a socket or a file or a buffer, a concept called AsyncWrite stream. And a few slides ago, we saw AsyncWrite stream. I named one of my template parameters that. So we get an AsyncWrite stream and we pass it to AsyncWrite. But there's no rule, there's no law that says that I have to pass through exactly the AsyncWrite stream I got. Maybe I could decorate it. I could decorate it to avoid this problem. So that when cancel is called, not only does it cancel all of the pending operations, but my higher level logic I'm going to layer on top in my decorator is going to be that cancel actually blocks future initiations. So when we miss, and AsyncWrite loops around and tries to initiate a new operation, that operation just fails immediately. And then when it fails, the higher level logic of AsyncWrite will bring AsyncWrite to a close, and that will call our write op, and that will bring our entire operation to a close. So let's write ourselves a sticky cancel AsyncWrite stream. We just store a reference to whatever we're decorating. We were storing a reference anyway, so this is of no consequence. And then we have our sticky bit, whether or not cancel has been called. It starts out as false. We provide a constructor and we pass through one of the required member functions of our underlying object, getExecutor. It's required by the AsyncWrite stream concept. Then we provide cancel with exactly the same signature as all of the I/O objects in the networking TS, and we just call through to the underlying object, but only after we set that sticky bit to true. Now, an AsyncWrite stream isn't really any good at all if you can't write to it. So we need to implement AsyncWrite sum on this type. There's a bit of networking TS boilerplate here, but the important thing to take away is that on lines 18, 19, and 20, if we haven't been canceled yet, we just pass through to the underlying object. We just act exactly like the user's stream does. But if we have been canceled, then we fall through to the bottom of this function. And there's some boilerplate here where we get an executor and get an allocator and form a lambda and then post that lambda directly to the executor and then fulfill our obligation to return whatever we deduce from our completion token. But the important thing is on line 26, on that lambda that we schedule for execution as soon as possible, where we take the user's final completion handler and we invoke it. We give it an error code that says you were canceled, and we also tell it that you wrote no bytes. And therefore, we close off that sharp edge that we left earlier, where possibly, maybe, sometimes we could just keep on writing for no reason. Because if that's going to happen, if we missed with our cancel, the sticky bit will be set to true. And then when AsyncWrite tries to initiate by calling this, it's just going to fail immediately, which means that our operation will be wrapped up. So now all we need to do is actually use all of this. So let's go back and modify the operation that we wrote. First, we're going to go into our state, and instead of storing a reference to the user's AsyncWrite stream, we're just going to wrap it up and store a sticky cancel AsyncWrite stream. Then we need to actually implement our cancellation logic. So we go into our write operation, and when we finish writing, we tell the timer, I don't need your wait operation anymore. Please finish it immediately. And then we go into our timeout operation, and we do exactly the same thing except for the stream. Except we're not canceling the stream, we're canceling the sticky cancel AsyncWrite stream, which means that even if we miss here, the operation will still bring itself to a close. Now we've actually composed in parallel and implemented a timeout operation. We've implemented that thing that people complained was so complicated to implement in the networking TS. But in so doing, I had to say to you, parallel composition. And that involves saying a dirty word, doesn't it? The word parallel. Because when you hear the word parallel, all of a sudden the specter of undefined behavior comes up, of happens before relationships and data races. How does parallel composition work in the face of this? Back in those halcyon days of series composition, we had this really nice guarantee where an operation would run and complete, and then it would start another operation. And this kind of causality is embedded in physics, not just computer science, which means that even if the underlying execution context had, say, 4 threads, well, there's only ever one piece of work for it to do at any one time because of this logical causal relationship between the operations. So we could just throw our hands in the air and say, oh, well, I'm not going to worry about parallelism. And that was exactly the approach I advocated for last year. But now we put 2 operations in progress at actually the same time. So if that execution context has 2 threads, then it's possible that both of those operations complete and both of their intermediate completion handlers get scheduled for simultaneous execution. And then they both go out and they try and access that shared state and that's a data race. That's undefined behavior, and now my program is doing who knows what. So there is a solution to this embedded in the networking TS. There's an executor type called strand. You layer it on top of another executor, and then the strand gives you the strand guarantee, which is that if you submit many pieces of work to me, I'll only ever allow one to run at the same time, regardless of the properties of the execution context associated with the executor it decorates. Everything appears single-threaded, which platonically is the solution. But the title of this talk says real world, not platonic domain. And in the real world, we might have a user who knows their application is single-threaded, who knows they're meeting the strand guarantee in some other way. And if we go and just blithely layer a strand on top of their executor, we're adding a bunch of synchronization queues and locks when they didn't need them. We're violating that fundamental principle of C++, which is you only pay for what you use. And so that brings us around to another approach to solving this problem. And that is pretty much a cop-out. We just document in the documentation of our operation that when you execute this operation, you must provide a completion handler which is associated with an executor which doesn't allow work actually submitted to it to run in parallel. And this cop-out actually has prior art. Basic stream from Boost.Beast, which is a library which implements HTTP using Boost.Asio / the networking TS, does exactly this. And if we look a bit deeper at basic stream to try and see, is this really a motivating example of what I should do? We'll find out that basic stream's shtick, the thing it does is it wraps a stream and then adds timeouts. So through the whole first part of this talk, we basically looped around and arrived at the same conclusion about parallelism that Vinnie Falco has. So we're in good company. But once again, the title of this talk said the real world. And if you just write something for your user and some documentation and run off, you'll be fine for like 2 weeks. And then you're the user. And now it's your problem again. So as we step up from the level of an individual operation to a higher level of our application, how can we manage parallelism in the networking TS? What approaches can we use to work around the fact that single-threaded code is really beautiful? It's really easy to write single-threaded code. It's really easy to think about single-threaded code. Single-threaded code has no locks. It's efficient and correct by default. But as with everything that's too good to be true, the real world has to come along and hit us in the face. And that hit in the face comes from ARM, AMD, and Intel. They say, well, I put a lot of cores in your CPU. So if you don't use them, you're not leveraging the whole machine. And not leveraging the whole machine is something that C++ developers don't like to do. So we loop around reflexively and we go back to what people have been doing for ages. We go back to an execution context. The networking TS provides one called IO context, which has many threads it can execute work on. You submit work to the execution context, and the execution context distributes it among many threads. And then at the highest level of your application, you're left trying to associate executors with things. You're left saying, okay, these 2 operations need to run on that strand, and these 3 need to run on that strand, these 4 on that strand, and so on and so forth. Do you really trust yourself to get that right? You're not going to mess that up and have a latent bug that takes years to find? But let's assume that you're perfect. Are you really going to be able to write down the structure that you've concocted, communicate it to the next person who has to maintain that code, and then have them, in turn, maintain it perfectly? Probably not. So maybe there's a different approach. Maybe we can flip this on its head. Maybe instead of having one execution context with many threads, we could have many execution contexts, each with 1 thread. Then everything we distributed to any of those execution contexts would appear single-threaded. We'd get all the beautiful benefits of single-threaded code. The only problem is that now we're left holding the bag. Whereas before we just kind of like dumped a bag of work on an execution context and it figured out where to run it. Now we're the ones figuring out where things need to run. But that's a blessing and a curse, because that means that we can put things in certain places and know that they always run single-threaded. And when we think about this, many problems in the real world actually have a way of distributing work that just falls right out of them. It may take on many forms, but let's think about a TCP server. A TCP server repeatedly accepts incoming connections. And most of the management of a TCP connection, reading and parsing bytes, managing timeouts, sending messages, that's all single-threaded. There's an implicit single threading there, but then there's also an implicit parallelism in the problem, because you accept many connections. And so each time you accept the connection, you can just distribute them across your pool of workers. Now, your program probably has some global state. It has some connection manager, so you can actually ask it who's connected. But you can factor that out into an independent component, add synchronization to that component, build confidence in that component, and use that component. Well, everything else you write now gets to leverage the efficient and correct by default guarantees of single-threaded code. All that we have to do now is we have to actually implement that round robin. And the class you use in the networking test to accept TCP connections is basic socket acceptor, and it provides an overload which does exactly this. We can call async accept, give it an IO context, give it a completion token. And then when it pops a socket out the other side, that socket is going to be associated with the IO context you provided, not the IO context that was provided with the acceptor. So now we just need to implement the logic on top of that, so let's write some code. We're going to start with the intermediate completion handler here, the code that actually gets run when we end our accept. We're going to store our acceptor and a triple of iterators, because we want the beginning and the end of our pool, as well as where we're up to in our round robining. Then, of course, we have our completion handler and this networking TS boilerplate that I've hand-waved away before. Which leaves us implementing the function call operator, the actual meaty part of this class. All we do in here is we bump that iterator. And if we get to the end, we loop it around to the beginning, and then we pass it through along with all the synthesized values to the user. Instead of just receiving a socket and an error code, the user receives a socket, an error code, and an iterator to the next executor they should use in round robining their work. Which takes care of what we do when we finish accepting, so let's actually get started accepting. We write the initiating function. It contains quite a bit of networking TS boilerplate, but the important thing to take away here is that it creates an intermediate completion handler type, and then just kicks off accept with that intermediate completion handler type and the result of dereferencing the current iterator. It dereferences it, gets an executor, gets the context associated with that executor, and passes that in. Then when this completes, since we already dereferenced and used that iterator, it's going to get bumped, wrapped around, and passed through to the user. And then the user can handle the connection however they want. They can do whatever they want with the socket, spin it off, start some asynchronous processing on it. And then they can call us again, and they can accept the next connection. And when I lay that formulation out, no one questions it. It's very unlikely that anyone said, well, you know what? In my workflow, I would really like to accept just one connection, but still round robin execution context. Because that doesn't really make any sense, does it? The way we've set up the round robining here pretty much implies that we're going to accept a lot of connections. And if we take a step back and we look at the model of work the networking TS has given us, we encounter a model that doesn't match the model that we have in the real world. Because at the very highest level of our applications, we don't say, okay, I'd like to accept one connection, I'd like to write 15 bytes, I'd like to parse one message and wait for 5 seconds. We say something like, I would like to accept every single connection. Then I'd like to send all of the messages, receive all of them, and wait for every single one of the timeouts. The networking TS presents us with this model, which is great for building up the building blocks of our application, wherein we execute a finite amount of work and then succeed or fail and we're done. But as we approach the highest level of our applications, as we bubble up to main, we enter a different domain entirely. We enter a domain where the pieces of work that we're trying to initiate are unbounded, where they go until they can't go anymore. Because we don't want to just accept one connection. We want to accept every single connection. And when you get a connection and you want to handle it, you don't want to just read the next message and process it. You probably want to read the next message and process it, and then the one after that, and so on and so forth. In some sense, both of these tasks, completely banal, go on until they can't go on any further. Which leads us to a conclusion for modeling our software at the highest level using the networking TS. And that's that maybe some of our operations, they don't need to be able to succeed. Because success implies that you're done and there were no problems. And a lot of networking tasks, well, they do finish. They finish because there was a problem. They finish because the connection was aborted. They finish because the client timed out. Or in the case of accept, the only really plausible example I can come up with is that they fail because the networking stack of the operating system went down. At any rate, these operations conceptually don't report success. And armed with the knowledge that this models our problems better than the model of the networking TS, we go out and look and see, hey, there's nothing that actually prevents me from writing an operation that never succeeds. It's not a requirement of the networking TS that the amount of work I kick off with an initiating function is bounded, or that it be possible for success to be reported. So let's leverage that very, very small composed asynchronous operation we wrote just last slide. Let's close the loop and write a powerful operation that eliminates the boilerplate of writing a TCP server once and for all. Here's the intermediate completion handler. Note that we kind of store the values that you would have expected from the previous slides. We store the acceptor that we're going to accept on, but now we don't need to store the current iterator. We store a double rather than a triple. And that's because we're going to rely on that operation we just wrote to manage that current iterator for us. Then we have this after accept object. It's a function object, which can be invoked with one argument. And we use it so that we don't consume responsibilities we don't want to. Because we just want to accept the connections. We don't really care what you do once they're accepted. And so we have this customization point so the user can inject the logic for actually handling each incoming connection. And then, of course, we have that lonely completion handler that we hope that we'll never have to invoke. We have this networking TS boilerplate, which we can pretty much just hand wave away. And then we have an initiate member function, which kicks off the next iteration of our asynchronous loop. It takes in the current iterator, and then notice how the last thing it does is move from itself. This is a fairly common idiom in the networking TS, and Vinnie Falco and perhaps others call it stack ripping. But at any rate, if we move from ourselves and also try and reference values resident in ourselves, that's implementation-defined behavior. And we prefer to avoid that, so we spend the 3 preceding lines picking objects out of ourselves, we kick off the call, and we move ourselves into that call, which means that we ourselves are going to be the one that handle the completion. And there's what that looks like. We're invoked by the operation we just wrote, so we take in 3 values, an error code, a stream, and an iterator. And then we have the sole completion condition for this operation. If the error code we get in is truthy, that means that we failed at accepting. And so only in that case do we invoke the user's final completion handler. Look as you may, you won't find another invocation of it. Assuming, of course, we succeeded, which overwhelmingly accept operations do, we're going to spin off that socket into that customization point. Because we don't really care what happens when we accept the connection. The responsibility of this operation was just to accept all of them. Then, once that's been handled, we close the loop. We call initiate on ourselves with the current iterator that was provided by the operation we're composing, which takes care of every single iteration except the first one. And so in the case of the first one, we're going to rely on the initiating function to get us going. We take in all the values you would expect, the acceptor, beginning and end iterators, that customization point, the after accept object, and the completion token. We lay out the networking TS boilerplate and we create an instance of our intermediate completion handler. And then we just call initiate with the begin iterator. Once we fall off the end of this function and return, we're off in the background, round robining over execution contexts, distributing work, accepting every single connection. We've managed to model the archetypal TCP server. We don't need any boilerplate in main. We don't need to copy paste from one network server application to another just to get things going. We have just one function. We call it with the right arguments and it basically executes our application for us. So as you leave this talk, what should you leave with? The first thing you should leave with is the fact that while the networking TS provides a framework with a lot of great guarantees, and while the real world appears to fight back against all such frameworks, if you take a step back and invest a little bit of time, you can reconcile the two. And if you do that, not only will you work around the sharp edges and solve problems in the real world here today, but you'll be synthesizing reusable components that solve those same problems and which can be tested and reused for all time. The end of copy-paste programming. The second thing we looked at was a class of problems that were not amenable to your archetypal series composition, that required that you bring asynchronous operations together and allow them to execute together simultaneously. We looked at the snags of that with respect to the bookkeeping that you have to perform and with respect to parallelism itself. And then regarding parallelism, we saw strategies for managing it. We saw how when you're writing low-level components, You just kick that can down the road. And then once you arrive at the highest level of your application, we have powerful strategies for dealing with that and injecting it and passing it down to all the levels of our application. And lastly, arriving at the very highest layer of our application, we saw a strategy for closing the loop, for modeling the kinds of things we see in the real world directly, the kinds of operations which perform an unbounded amount of work, which continue forever once put into motion unless they fail. And that gave us the possibility that rather than our main function being a bunch of repetitive glue code that closes, loops, etc., we might be able to implement our main function as just one call to one initiating function for one highly reusable, highly tested asynchronous operation. Are there any questions?
There are a lot of, do you hear me? Okay. There are a lot of ways, framework for networking and so on. For example, there's one libv that we use in 2011, 2012 for the I/O printer with event loop. Why do we need so much complexity in this case? Because you have seen that you related, you get from the past the proactor pattern and you go ahead in the same way. It's not too complex for debugging that. Why do we need such complexity? Because when the cases goes very well, it's fine, we are very happy. But when you have to debug networking code in a proactor, it's very hard, in my experience. What do you think about?
Well, there's a couple problems layered in there. Like the one is, why do we need this much complexity, right? And one of the things that falls out of that is that a lot of the complexity in the networking TS is actually glue code, right? Which is something that you can mitigate through strategies that I considered putting on these slides, but it just made them blow up because you'd have to like bootstrap yourself from first principles, basically. So you can eliminate a lot of that glue code that way. The other issue is that the networking TS being like a TS and going into the standard and Asio trying to be a framework is that you're basically trying to not just solve today's problem today, you're trying to solve the problems people think of in the future. For example, if you could constrain yourself when you're writing networking TS applications to basically using the dispatch method that Node.js uses, always single-threaded, like we wouldn't have to worry about most of this stuff, right? Because we would know that things never run in parallel. We'd know that nothing else is running when we're running. We wouldn't have any data races. But it's when you throw in the possibility that the user knows something you don't and is letting your stuff run in parallel that you end up with all this complexity. And then when it comes to timeouts, one of the reasons why timeouts themselves are so complex is because, again, the networking TS is trying to take and provide a cross-platform abstraction for timeouts. And so while most platforms with blocking writes and reads, they'll have a parameter you can set kind of behind the scenes that allows you to time it out, asynchronous operations don't really provide that. Like, as far as I know, I could be wrong because I haven't written completion port code in a long, long time. You can't call like sendx and begin an overlapped send and tell it to time out.
No, because the completion code has an handle and it has a timeout as well. You're right. Thank you.
Hello, thanks for the talk. I have a question about coroutines and this executor model. How well they cooperate? Because I've seen few talks about coroutines, and they have some cowait, cora, coreturn, and std feature and when. How these two models will cooperate or will live together in STD?
Right. So a lot of the boilerplate, like kind of the meat of that, is covered in. Well, last year I talked about the universal asynchronous model, and the reason I called it that was because that's the title of a paper that Chris wrote a long time ago about the completion mechanism in the networking TS. And basically the stuff that I hand-waved away today, the completion tokens, what that does is it provides a framework where instead of like getting a callable object, which you invoke when you're done, you get in this token, and then there's a customization point in that token where you split that token apart, and you get an actual completion handler and a return value for your initiating function. Now, most of the time people are like, here's the function, right? And so the completion handler is just a function and the return type is void. But you can do other way more complicated things, like you can transparently turn any compliant initiating function and the corresponding operation. You can just pass in a token that in the case of Boost is Boost.Asio use future. You pass that in, all of a sudden, instead of returning void, that operation returns a future, right? And I believe, from what I've seen, and I don't know what version it went in, but at least in Boost 1.77, Asio has a token that you can pass in that's called use awaitable. You pass it in, and all of a sudden, right, you can use coroutine operations on the outside of that asynchronous thing. The deal with executors is executors are just a way of giving the code somewhere to run, right? Because we experienced this with std.async. One of the things, there's a lot of them. One of the things that's wrong with std.async is that when you call std.async and you launch something, you have no idea where it's going, right? Like, where are those threads? Whose threads are they? Who's managing them? You have no idea. And a lot of times users want to actually know where their stuff is executing for good reason. And so all an executor is, at least in the conception of the networking TS, because there's also executors themselves, and they're trying to be reconciled together. That's one of the reasons that networking didn't get into C++20. So all you're doing there is you're providing the context that you run in, right? Because I come from HFT, and in HFT, the thing that you care about is what core is all this going on? Not just how many threads do you have or what overhead there is, but like, I want to pin this to this core. And if you use like std.async, how do you pin something to a core when you don't know what thread it's running on? Whereas when you just provide this context to execute in, you can pin that thread to a core, and then you know that all the work is going onto this core. That's something that I do in applications we write at work every day. I take, in older versions of Boost, it's called IO service. It's called IO context now. I put a thread in it, I pin it to a core, and then I know exactly where it's running. So I think they solve two different things, right? Like the coroutines is how we inform you that the operation is done, right? So you can integrate it basically into code that looks synchronous. And then the executor basically gives you the behind-the-scenes context that actually gets that work done.
Okay, thank you. And I have another question is, will there be a TLS support from Boost in STD library?
Sorry, what was that?
Will there be the TLS support in STD's library?
I'm not sure what you're asking.
The Boost has the TLS.
Oh, TLS support, right. I don't think that's in the networking TS right now. So for that, you have to use Boost. Yes. Which I don't consider that to be particularly onerous, but maybe in the future they'll get it. And the thing about the networking TS itself is that it's kind of a pain, but you're not limited to just the types the TS gives you. Because as long as you understand the behind-the-scenes machinery, you can actually glue in and write your own I/O objects. So either you can just keep using Boost, right, if you need TLS, that's a compelling option, right? Or two, you can write your own TLS stream using OpenSSL, which looks like the networking TS and it's the same thing. That's number two. Or number three, like someone's going to take the one from Boost and port it, so you can just download it as like a header-only library or something like that. But for now, they don't have TLS in. A lot of things that are in Asio and are really cool and really useful aren't in the networking TS. Like there's a class for basically performing asynchronous I/O, except the I/O you perform is getting a signal. That's not in the TS either.
Okay, thank you.
So you were doing your move from this. How do you stop it? Is you expect the user, like if you want to stop accepting because you got a shutdown and you want to finish off your current connections, right? So you're moving your acceptor around, right? Now you probably lost a reference to it, or do you have like a shared pointer somewhere? How are you managing that? Or do you expect in the after accept that the user throws an exception?
So the question was related to what do you do with the acceptor? Like you're often in the background and you're accepting all these connections, and now you want to actually like gracefully shut your application down. But, and I think this was the important takeaway from your question, but you want to make sure you finish out all of the connections.
Yes.
So what you can do in that case, right, is barring parallelism, because parallelism adds a layer of complexity onto these problems. And the way you get around parallelism typically is you're like, I have my single-threaded execution context, right? Say the one that the acceptor is associated with. And I need to do something to the acceptor. But maybe something in that execution context is using the acceptor. So that would be a data race. So what you do is you take your operation, you put it in Lambda, and you post it into the execution context, right? So that's how you can kind of like, and then we're not moving the acceptor around, we're just holding onto a reference to it. So the acceptor itself stays in main. And so then what you can do is you can post yourself into the execution context, which is single-threaded, so you know that no one's racing with you on the acceptor. And then you could just call close on the acceptor. And when you call close on the acceptor, it actually goes and closes the underlying file system handle and causes, it's basically like canceling, right? All of a sudden, the pending operations on the acceptor will fail, which means that the whole operation we wrote fails, which means that your completion handler gets called and then you can do whatever you want. But because we spun off every connection with after accept, they're unaffected, right? Unless, the logic of your application dictates otherwise. Because you can do something like you can throw from after except if you want, right? If you get a connection and, the connection's from a magic IP, that means shut my application down, you can just throw. And then that percolates all the way up and is handled however the executor handles it. And the executors and the TS handle exceptions by throwing their hand in the air and just letting them pass through.
Okay, thank you.
The other question is about the threads. So you have an executor where you pass some acceptors. My question is about an embedded environment, for example, with an high frequency speed, connection, opening, close, and the memory consumption. What about that?
So I've never had a reason to profile the built-in execution context. It's always, I work in HFT. So for all the stuff that is really needy, we just go off and we spin. And so I've never really encountered a problem where that was a problem. We do have some libraries that use the networking TS for something vaguely resembling trading operations, and it's fast enough there. But this is the other great part about the networking TS, is that if the networking TS provides you with something and your vendor's implementation of it is not up to snuff, most of the stuff throughout the entire TS, and that kind of comes back to your complexity question earlier, most of the stuff in the TS doesn't really care about what the type is, it cares about the concept. So if you get really upset with the built-in execution context, you can write your own. Right? I've actually written my own execution context, and it can dispatch work however it wants. It can have whatever limitations it wants.
So you have a lot of flexibility.
Exactly, and that's a lot of the complexity and boilerplate in the TS comes out of the fact that they don't want to pin you down. If you want to execute on this executor, we'll go for it. If you want to do this, go for it. If you want to complete this way, go for it. And that leads to a lot of boilerplate, but leads to a lot of power.
So this goes exactly in the C++ philosophy, pay what you need.
Right, exactly, yeah.
You may have answered this already. I came in late, so I may have missed it. But other than the namespace, how close is Boost.Asio to the networking proposal?
In terms of my exploration of what I understand is the current TS, so I pulled it from, I forget where I pulled it from, but I tried to find the latest TS. And then I consulted, when I was writing all the examples, which you can find right there. They're fully worked. There's even more than were used in the slides, because I developed 6 examples that I didn't end up using. If you download them, run them, they run and execute. But when I was looking at documentation to try and figure out, okay, what exactly do I need to do here? I always just read the TS. And so in my experience, as best I've been able to tell, there could be 1 or 2 issues here. Asio is a strict superset of the networking TS, because it has everything the TS has, as far as I can tell, and then way more, especially if you're working with signals, or the other example is Windows handles, right? The Asio has all these classes for asynchronously dealing with Windows handles because its backend is completion ports, and so that's easy. But the TS doesn't have any of that.
So there's no conflicts between the networking TS and Boost.Asio where they overlap?
Right, so there's no conflicts, at least to my understanding, and at least right now, right? Because the TS might continue to evolve, and Asio might, well, Asio is trying to track the TS, basically, for now. But I think my sentiment that I've gotten from talking to several people who have been involved in the standardization is that people are pretty happy with the networking TS. It's trying to get the backend stuff to play well with executors so we don't end up with 2 ways of doing the same thing, which would be a tragedy since they're both on standards track at the same time.
Thanks.
That's all the questions. Thank you very much.